Hi everyone, this is Aidan for Fluid Mechanics 101, and in today's talk I'm going to be talking to you about Green-Gauss Node-Based Gradient Schemes. This talk is going to wrap up my recent set of lectures on gradient schemes, so you're finally going to have a complete idea of what the cell-based, node-based and least squares gradient schemes actually do in CFD codes, and also have a good idea about what scheme you should select for your application. So sit back, pay attention, take some notes. I know you're going to find this talk extremely useful. So the first thing we need to think about when we're thinking about gradient schemes is a reminder that the majority of mainstream CFD codes, such as OpenFOAM, ANSYS Fluent and StarCCM, calculate and store the flow variables, so velocity, temperature, pressure, at the centroids of the cells, and you can see that in the diagram there. All the information is calculated and stored at the cell centroids. Now, once we've calculated those flow variables, the velocity, temperature, pressure fields, and other fields, we'd also like to calculate the gradient of those fields at the centroids of the cells. And just as a reminder here that temperature and pressure are scalar fields, so when we calculate the gradient of these fields, we're now calculating a vector quantity. And just as a quick reminder for you there, in equation 1, the temperature gradient of course has three components, and in Cartesian coordinates, which the majority of CFD codes use, that will be the temperature gradient in the x, y and z directions. So we've gone from a scalar field to a vector field, and we need three components there. Now, how are we going to go about calculating the gradient of these schemes at the cell centroids? And as another reminder for you, why do we need the gradient in CFD codes? Well, we need it for some discretization schemes, such as linear upwind differencing, for example. And I've got an example of that scheme for you in the diagram, which you can see on the screen there. And the way the scheme works is that we want to calculate the face value of the temperature, TF for example, and the way we do that is by taking the value at the cell centroid, TP, and then adding on the gradient there, which you can see grad T evaluated at the centroid and dot producted with the vector between the cell centroid and the face center there. So we're using the gradient to extrapolate and work out what the face value of the temperature is there. We also need the gradient when we're evaluating non-orthogonal correctors on non-regular meshes, and we also need the gradient at the cell centroid for some source terms. So there are a variety of reasons why we need the gradient at the cell centroid. But the important thing to remember here is that at this point in time, we know what the value is at the cell centroid, TP. We know what TP is, and we'd like to use that to calculate what the gradient is. That's grad T here. And throughout this talk, I'm going to be using the temperature field, just because I find temperature an easy variable to look at. It's very straightforward to follow, and it helps with your understanding for what's actually going on, rather than using an arbitrary field such as phi, which a lot of people actually use. So I'm going to be using temperature throughout this talk, but of course you can replace temperature with any other flow variable that you're looking at. So there are different methods of calculating the gradient, and the way you select the gradient scheme will vary depending on what CFD code you're using. Now, if you're using OpenFOAM, for example, if you open up the FV schemes file, you'll find a dictionary entry called grad schemes, and in there you'll find entries where you select the type of gradient scheme that you would like to use. So in this instance here, you see grad U, and we're using a point linear scheme, and that's OpenFOAM's way of saying we're going to be using a Green-Gauss node-based gradient scheme, which we're going to be looking at in this talk. And in the screenshot there, you can also see the top drop-down menu there is where you select the gradient scheme in ANSYS Fluent. And in this case, a least squares cell-based gradient was used. So in most CFD codes, you have to select the type of gradient scheme that you'd like to use. And in this talk, we're going to be going through the node-based gradient scheme. And in previous videos, I've released and gone through the cell-based gradient scheme and the least squares gradient scheme. So if you'd like to learn how those schemes work, I'd advise going back and having a quick watch of those videos. So to start things off, I'm just going to give a quick recap of the Green-Gauss scheme, because this is what the Green-Gauss Node-Based Gradient Scheme is based upon. And in the Green-Gauss method, the way we calculate the gradient at the cell centroid is using the formula which you can see in equation 3 there. And if you'd like to know how this formula is derived, I've put the complete derivation in my previous talk on the Green-Gauss cell-based gradient scheme. So if you haven't seen that, or if you've forgotten, I'd highly advise just quickly flicking back to that talk and having a look at the derivation. But what the formula says is that the gradient at the centroid, that's grad T, P, is equal to the summation of the face values of the field that we're interested in. So in this case, you can see that you've got TF, that's the temperature at the center of the face, multiplied by the unit normal vector on the face and multiplied by the area of the face. So what we do to evaluate the gradient is go around each of the faces of the cell, and for the image in the diagram here, you can see we've got a pentagon, so we've got 5 faces, and on each of these faces we take the face temperature, TF, multiply that by the unit normal vector and the area of the face, and then we add all the faces up and divide by the volume of the cell, and that gives us the temperature gradient at the centroid of the cell. And a quick check here shows that by multiplying by the unit normal vector, you can see that we're now going from a scalar temperature field to a vector temperature gradient. So the unit normal vector will allow us to get components in the X, Y, and Z directions. And if you go through my previous talk, you'll see an example there of where I've used this formula, and so you can see how it works for a simple example. Now, this is the Green-Gauss scheme in general, and what you can see here is that we have a method of computing the gradient at the centroid of the cell. However, we need to know what the face values of the temperature field is, so TF. We need to know what the face values are, and once we know the face values, we can substitute them into the formula and then calculate the gradient. And so we need a method of calculating the face values from the centroid values, because we know what TP is. We've either solved our CFD solution or we've carried out an iteration, and so we know what TP is, but we need to learn what TF is. And this is where the difference between the cell-based and the node-based gradient schemes come in. They're different methods for computing the face temperature TF. And in today's talk, I'm going to focus on the node-based scheme. And so the procedure that we use overall for calculating the gradient at the cell centroid using the node-based scheme is we start by computing the nodal values, that's the dots which you can see in red in the diagram there, from the centroid values, and then from the nodal values, the red dots, we calculate the face values, which are the green dots, and then we can use the Green-Gauss formula in the previous slide to calculate the gradient. Now, throughout this talk, I've used a consistent color notation to help you as you follow along. And throughout, what you'll see is the centroids are colored blue, the nodal values are colored red, and the face center values are colored green. So this should help avoid any confusion. And this slide is just a reminder for the overall process for how the node-based gradient scheme works. We're going to start by calculating the nodal values, the red dots, then the face values, which are the green dots, and then the centroid gradient. That's in blue there. So that color scheme will stay consistent throughout, and it should make it a bit easier to follow. So how do we calculate the nodal values? Well, there are different methods we could use, and one method we could use is we could just take the average of the centroid values that surround the node. And the way I want you to think of this is if you look at the small sketch there that I've got on the slide. Now we've got a node in red, and we've got 5 cell centroids shown with blue dots that surround this node. Now this is a different way of thinking about and looking at CFD meshes, because often what we do is we focus on the centroid and then look at the cell that's around it, but this time we're going to be looking at the node you can see in red there. And what you'll notice is that the node can be surrounded by a large number of cells, and the cells don't necessarily have to be the same shape, the same type, or the same size. And in this instance, we've got quadrilateral cells on the left and we've got triangular cells on the right. But for this particular node here, which you can see in the center, it's surrounded by 5 different cell centroids. And the way we could calculate the temperature at this node is just by adding up the temperature at those 5 centroids there and then dividing by 5, so that we have the arithmetic mean there. And that's one method we could use. So just to write this out fully, TV, that's the temperature at the node or the vertex, would be 1 over 5 multiplied by the summation of those 5 temperatures. Now, this is one method that we could use to compute the nodal values. However, I've used this quite unusual example of cells, which you can see there, to really emphasize the problem with this method. And the problem with this method is that you can see that the centroids 2, 3, and 4 are actually a lot closer to the node than the temperatures at centroids 1 and 5. And so just thinking about this, we'd expect the nodal value to take a temperature that's a lot closer to T2, T3, and T4 than it is to T1 and T5. And so actually, if we just used a normal averaging technique, which you can see here, we'd get the wrong temperature at the node. And what we really want is we want to somehow weight the temperature at the node by the centroids that are closer to it, so that if we have an extreme case like this, which you can see in the diagram, that our nodal value will be correct. And the reason this situation can come up is because the nodal value is not necessarily at the centroid, is not necessarily at the center of the cells that surround it. One node can be connected to any number of cells, which could be any shape or size, and so often situations like this arise. And just remember that this is not the case if we're thinking about centroids or faces of cells, because the centroid is always going to be at the middle of the cell, and likewise the face center is always going to be at the center of the face, but the node is not necessarily going to be at the center of the cells that surround it. And this is why we have to use a slightly different treatment. And the way we calculate the nodal value is we use a simple weighted averaging. And what we do is we weight the contribution of the temperatures by 1 over the distance in the summation. And don't worry, I'm just going to take a minute now just to explain what that is so that you really understand. What we physically expect is for cells that are closer to the node to have a larger contribution. So what we do is we multiply by 1 over d, where d is the distance between the centroid and the node value, which you can see there in the diagram. So those two centroids, which are quite far away from our node, are going to have a smaller contribution than the cells that are closer to it. And then, so what we can do is once again evaluate the simple summation there in equation 6, and that will allow us to compute a nodal value from the surrounding cell centroids. And just as an example, using the same shape that we did before, in this instance TV would be equal to the summation, which you can see there on the top, T1 over D1 plus T2 over D2 plus T3 over D3, and so on. Noting, of course, that we use a different distance for each node because, for each centroid, because each centroid is a different distance away from the node there. And of course, in the case where each of the distances is the same and the node happened to be at the center of the surrounding centroids in a structured mesh, for example, of squares, then this would just return to the normal averaging formula. So just to summarize there, we use weighted averaging to compute the nodal values from the centroid values of the surrounding cells. And when we do this, a few of you who've been following along quite closely will realize that we now in our CFD code need to keep some kind of a record for which cells surround each node. So we have to store a bit more information in our CFD code and be quite clever so that each node knows not only which faces it's connected to, but also which cells surround it as well. So for those of you, if you ever decide to write your own CFD code, you have to think quite carefully about how you set that up. So now we've got the nodal values, the next thing we do is calculate the face center values. And remember from before, I'm using a red dot to show where the nodes are and a green dot to show where the face centers are. Now, unlike the nodes, which we just looked at, the face center is always going to be at the center of the face. And so for that reason, we can use a standard averaging. We don't need to use any weighted averaging to calculate the face center value from the nodal values. So in this case, where we've got a cuboid there and we wanted to work out what the face center value is, TF, what we would do is we would just add up the temperature at those 4 corner nodes and then divide by 4, and that would give us our face center value. And repeating that process, we'd now be at a point where we know all of the face values for our cell, and then we can go back and use the Green-Gauss formula to work out what the gradient is at the cell centroid. So just a quick summary of that procedure, because it might have been quite a lot to take in. In the Green-Gauss node-based procedure, what we do is we start by calculating the nodal values from the cell centroid values, and we do this with a weighted averaging to account for centroids that are further away from the nodes. We then calculate the face values by using standard averaging, and then finally we use the Green-Gauss formula to calculate the gradient at the centroid, which you can see there at the bottom. And just by comparing those formulas 9, 10 and 11, you can see that we have to sum over cells, we have to sum over nodes, and we also have to sum over faces. So we want to think quite carefully about how we set up our CFD solver if we do that, so that we have the ability and the capacity to iterate and loop over cells, nodes and faces. So clearly that's where a lot of the work has to be put in for CFD code, just thinking carefully about how this data structure is organized. So now I'm just going to move on to talk a little bit about boundary cells, because if we think about nodes and face centers that are on the boundary, they only have cells on one side of them. And so you might think, oh, perhaps we have to use a different treatment for these node or face center values. Well, actually, the treatment on boundary cells is very simple. And the reason for that is that we assume that for each cell, the boundary temperature or boundary quantity, whatever we're looking at, is constant across the face of the boundary cell. So in the small diagram you can see here, we've got a boundary at 200 degrees C, and what that would mean is that the nodes, the red nodes and also the green face centers are all at a temperature of 200 degrees C. So we can take those face center values and put them straight in to the Green-Gauss formula to calculate the gradient at the cell centroid. We don't have to do any averaging like we looked at in the start of this talk. We can just go directly to the Green-Gauss formula and use that to work out what the gradient is at the cell centroid. And I've just made this explicit here in the two expressions you can see at the bottom. TF and TV are both 200 degrees for those cells. To wrap up the talk, I just want to make a small comparison between the Green-Gauss cell-based and Green-Gauss node-based gradient schemes. So this is going to be useful for you when you come to select the gradient scheme that you want to use in your CFD code. Now, if we think about the cell-based gradient scheme from a previous video that I did, what you might remember is that we take the values at the cell centroids, the blue dots there, and we use those values to directly calculate the face center values. So we don't calculate the nodes, we calculate the cell face values directly. And what you can see in the diagram is that this can cause a skewness error when we have two cells that are connected in a skewed fashion. And remember, of course, that this is a skewness error. This is different to a skewed cell. A skewed cell applies to a single cell that may have a weird irregular shape with either small or very large angles. But the skewness error is associated with two cells that are connected by a face. And the reason the skewness error arises for the cell-based scheme is when we interpolate directly from those cell centroid values, what we're actually doing is moving along the black arrow, which you can see there in the image. And the value calculated on the face from the cell-based scheme is actually at that intersection point there, which you can see with the green dot, which is highlighted. But if the cells aren't aligned well, we can see that actually this calculated value doesn't occur at the center of the face. There's a slight offset in where we've calculated the values. And the reason this is an issue is, of course, in the finite volume method, quantities vary linearly across faces and also linearly across cells. So if we knew what the values were at the nodes, the temperature field would have to vary linearly along the face, or along that blue line which you can see there in the diagram. And because it's varying linearly, our intersection point is not quite at the face center, and this will result in an error in the temperature field prediction on the face. Then when we carry that through to the Green-Gauss formula there to calculate the gradient at the cell centroid, we'll have a slightly erroneous calculation of the gradient at the cell centroid. However, if we think of the node-based gradient scheme, because we've calculated the nodal values in red first, while this does require us to do an extra calculation, when we use averaging to calculate the face value, we are in fact computing the value at the face center. And so the node-based gradient scheme doesn't have a skewness error that the cell-based scheme has. However, of course, as we've seen from this talk, the node-based scheme is slightly more expensive to calculate, as we have to calculate those nodal values every time we want to calculate the face values and then the gradient. So it's slightly more expensive, and we also have to think quite carefully about how we set up our CFD code so that our nodal values know which cells they're connected to. So that just about wraps up the talk. Just a quick summary of what I've talked about today. When we use the Green-Gauss node-based scheme, we use a weighted averaging procedure to calculate those nodal values, and the reason for that is that some cell centroids of the surrounding cells may be closer to the node than others. There's really no restriction on which cells can be connected by the nodes. And the node-based scheme, of course, is more accurate than the cell-based scheme, as it doesn't have that skewness error, which we've seen previously. And always take care to remember the difference between the skewness error and a skewed cell. The two are very different things, and it's very tempting because we always see skewness as a metric reported by our meshing programs to get confused between the two, but a skewness error is something quite specific. And of course, just to finish off, the node-based scheme is slightly more expensive than the cell-based scheme, and it's slightly more complicated to set up. However, with, of course, modern computers and modern CFD codes where this structure is already built in and sorted out for you, there's really no real reason to use the cell-based scheme over the node-based scheme based on what we've seen in this talk. Now, for those of you who've seen my previous talk, you'll remember that there are some instances where the cell-based scheme and the least squares scheme have some differences in accuracy, and that's for very specific flows with thin boundary layer cells. And if you'd like a comparison of those schemes, I'd advise you go back and watch my previous videos. So that brings us to the end of the lecture. I hope you guys have found it extremely useful, and it also brings me to the end of these recent series of lectures that I've been doing on gradient schemes in CFD. And hopefully by following along with these lectures, you've now got a really good idea of what the differences are between the cell-based, node-based and least squares gradient schemes. So when you select them in your CFD code, you actually have a good idea of what's going on. And currently at the moment, I'm working towards putting together another online course, which this time is actually going to go and dive into unstructured CFD meshes, and actually taking you through a worked example of how you can set up a CFD code in an unstructured format to use cells of any shape and size, and to take that all the way through to a CFD solution. Because currently what I've been able to produce and what I can currently find on the internet, the CFD examples are always based around very simple structured meshes with rectangles and structured grids, and it's really not very helpful. And I think something that would be fantastic for us in the CFD community would actually be to start to have some useful, simple examples of how you can run things with an unstructured CFD grid with triangles and other shapes, and really help us to develop our understanding about how these concepts of gradient schemes and non-orthogonal correctors and such are actually working. So I'm currently working on putting that together, and I'm going to be really excited to bring it to you guys. I know you guys are going to love it, but of course it's taken me a little while to do because it's quite difficult and hasn't been done before at all, so I have to be very careful when I'm working through and checking it through. But just wanted to let you guys know that that is on the horizon and will hopefully be coming towards the end of the year, and of course you guys will be the first to know about that. In the meantime, if you guys are interested in my my other courses, you can pick those up on my website, which is linked in the description below, or even follow the courses on Udemy. Many of you have been telling me that you particularly enjoy following the courses on Udemy, so if you haven't, go ahead and try out the courses on Udemy. I know you'll like them. It's looking at taking CFD examples from first principles, very simple examples, so you can actually see everything about how the solution is developed and how you set up the code. So yeah, if you haven't checked those out, go ahead and check those out. And I know you guys are going to find this new course that I'm working on absolutely fantastic. It's going to be a real game changer and not one that I've seen yet anywhere on the internet. So you guys have got that to look forward to. And in the meantime, of course, let me know, did you guys like the video? Do you like the content? Are you finding it useful? What other things would you like to see? Because as you can probably tell, I'm trying to really address all of the main areas in CFD where there really is a lack of information out there online and on the internet. So if you have any good ideas or things you'd like to see, leave them in the comment section below. Let other people comment. Let's open up the discussion and really try and improve the value of the CFD content that we have out there for everyone. So until next time, thanks again for your support, guys. I really appreciate it, and I'll see you next time.